Hello, mathematicians. We have finally reached the end of Unit 1 with this curriculum, and we are going to review key concepts about scale drawings. So before we get into this, there are a couple of things I'd like for you to do. One, when you're watching this video, I'd like for you to take some notes, and I will tell you what to write down. Essentially, you're going to write down what the key concepts are and any additional notes that you find might be helpful in your notebook. And so without further ado, let's begin. We are going to start with a song and a jingle that's going to help you remember the key characteristics of what scaled copies are. So here are the two characteristics of scaled copies.
You know what time it is. It's time to learn a lot of math with a cool song. And it's called Scaled Copies. Scaled Copies. Scaled copies. What? All lengths are multiplied by the same scale factor. All angles are the same measurement. Scaled copies. Scaled copies. All lengths are multiplied by the same scale factor. All angles are the same measurement. Scaled copies. Scaled copies. Geometry.
Okay, so if you want to watch that video in its entirety, you can go to youtube.com/MathwithMrAlmeida and look up scaled copies. However, the main takeaways from that video, you're going to copy down these key concepts in your notes. All lengths are multiplied by the same scale factor. If you indeed have a scaled copy of an original, then you are going to be multiplying all lengths by the same scale factor, and all corresponding angles are going to have the same measurement. So all corresponding lengths will be multiplied by the same scale factor. These are corresponding lengths. These are corresponding lengths. You would multiply the length of the original by the same scale factor to get the scaled copy length. And the angles of a scaled copy are going to have the exact same measurements as the angles of the original. So these are your two main concepts about scaled copies. To illustrate this, let's take this as our original. And we are going to take this drawing and we are going to multiply the original side length by 2. So the scale factor that we're going to use that will multiply all sides is 2. So we'll take twice the length of this length, twice the length of this segment, twice the length of this, and this segment. So all segments will be multiplied by 2. If you look here, this has a length of 2 units, and I would multiply that by 2 to get 4. I multiply this length right here by 2 as well. Right now it's 1, 2, 3, 4, 5, 6 units long. So it will be 12 units long in our scaled copy. Let me show you how that would work. I would make sure that this was 12 units long. So right now this bottom piece is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units long. Let's make it 12 units long right there. So this essentially would be multiplying all of the side lengths by 2. Because if I multiplied one side length by 2, if I have the entire drawing, all side lengths have been multiplied by 2 units. And if you see, if we actually did the measurements, you'd be able to see that we would get this would be 1, 2, 3, 4, 5 units. This should be 10 units long. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then these units right there would make it 10 units long right there. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units long. And that's this length. So just multiply all side lengths by the same factor. The number you multiply the side lengths by is called the scale factor. Let's move on to thinking about some information if we are trying to find what the scale factor is. says that Diego and Jada want to scale this polygon right here. It's just a closed shape, so that the side that corresponds to 15 units, so this side right here, is now 5 units in the scaled copy. Well, when thinking about scale factor, you want to figure out what you're multiplying one number by to get the other. So I always make a table. One column is called the original, and the other is called the scaled copy. And in this case, we're dealing in general with just units. So if the original had 15 units long, and the corresponding side that it was matching with is 5 units in the scaled copy, what number am I multiplying 15 by to get to 5? Well, some of you would say, what am I dividing by? You can think about that, but I also want you to think about what is the factor that we're multiplying it by. So yes, we do divide 15 by 3 to get 5, so let's see that. We divide 15 by 3, and when we do 15 divided by 3, we get 5. And then what number times 5 will give us 5? 1. So we're multiplying by 1/3. 15 times 1/3 equals 5. So the scale factor is going to be 1/3. If, for example, you need to find the perimeter of an original figure, and if you look at this original figure, there are some side lengths that are missing, namely this length and this length right here. If you are missing vertical lengths, then I'd like for you to focus in on the vertical lengths that are parallel to that. So the vertical length that's parallel to this, that means they're the same distance from each other no matter which point you look at, is this length right here, so a length of 12. So from here to here is a length of 12, and from here to here is a length of 18. So just take that length and move it parallel to itself. It's 18. So then what is the length of this entire segment right here? Well, 12 put together with 18 makes 30. So this length right here is a length of 30. What if you are missing this length right here? This length is, if I draw it parallel to itself, I'm going to use all of the horizontal lengths. So the distance from here to here is also the same distance from here to there. Okay? And do I know the distance from here to here? Well, let's look at the opposite side right here. Is it labeled for us? Yes, it's 15. So this is 15 units long. And do I know this length right here? No, I don't. But I do know that from here to here is 36 units long. So to find this missing length right here, I would simply be taking a length of 36 and subtracting 15 from it, because essentially I'm asking 15 plus what number equals a length of 36. And when I do that subtraction, I end up getting a length of 21 units long. So if this is 21 units long from here to here, which is parallel to that, is also 21 units long. And if you look at our drawing, we do have the exact same measurements here. So that's what you do if you're missing the lengths of sides. Now again, to figure out perimeter, I would add up all of the lengths of the sides. So 36 plus 18 plus 15 plus 12 plus 21 plus 30. And that would give me the perimeter of this figure. Next, the other key concept that we want to think about in this unit is if we want to determine the area of a figure, we want to see how it relates to the area of a scaled copy. So this is going to be true every single time. The area of the scaled copy is always whatever the scale factor was. So if your scale factor is 5, you're going to square it. That means 5 times 5 will be 25. So the area of the scaled copy would be 25 times the area of the original. Say the scale factor was 3. Then you would square 3, and you'd get 9. So the area of the scaled copy would be 9 times the area of the original. Let's see what happens in this case. Well, if this is the original, I first have to figure out what the scale factor is. To do that, I look at the lengths of corresponding sides. So if this length right here is 10 units long, the side that is in this exact same position in the copy of the rectangle is this length right here. So what do I have to multiply 10 by to equal 5? Well, I have to multiply it by a number that's less than 1, because 1 times 10 is 10. So if I think about this, 5 is exactly half of 10. So I'm going to multiply 10 by 1/2. What does that essentially mean? It means I'm taking the number 10, dividing it by 2, that gives me 5, and then I'm multiplying 5 by 1, and that's equaling 5. So that's what I'm multiplying 10 by, 1/2. If I want to find what the area is compared to the original, it's only going to tell me how the area is multiplied by the original area. So if this area right here, say, is a given number, what will this area be compared to this? Well, I'm following what my general takeaway is, and the rule says that the area of a scaled copy is always the scale factor. So what is the scale factor in this case? 1/2. And I'm going to square that. What does that actually mean? It means multiply 1/2 as a factor 2 times. So once, twice. And when I multiply fractions, I'm thinking of the product formula, which says multiplying 2 fractions is the exact same thing as multiplying the numerators and then multiplying the denominators. And so I get that the area of the scaled copy should be 1/4 of whatever the area is of the original copy. And so let's see this in action. Yes, I can calculate what the area of a triangle is. If you remember, area equals 1/2 base times height. The base is 6 units. The height is 8 units. I would get the base times height would be 48, and then I'd multiply that by 1/2, and I would get 24 units squared. So this should be 1/4 of 24 units squared. If I do this, I get 3 times 4 is 12, and then 12 divided by 2 is 6 square units. Is 6 1/4 of 24 square units? Yes, it is. And to illustrate that even further, let's take a look at this picture. If this is true, this represents the area of the scaled copy. This area right here should be 1/4 of the area of the entire original drawing. So let's see this in action. Okay, so there's one of those triangles. If I were to rotate this and put it right up against it, this would be 2 of those rectangles. 2 of those triangles, I'm sorry. And then another triangle could fit right there, and another triangle could fit right here. I wish that these didn't block each other, but the idea is that this area right here, is going to be 1/4 of whatever this area was. So you can imagine one here, one triangle there, one triangle here, one triangle here, and the other triangle here. So you can see that the area of the scaled copy is 1/4 of the area of the original, thus proving the general rule that always follows when you're trying to find the area of a scaled copy. You're going to square the area of the scaled copy is going to be the scale factor squared times the area of the original. Okay? All right, our next key concept is this. When we're dealing with scale drawings now, Scale drawings are going to be two-dimensional representations of actual objects or places. So these are going to be something like floor plans. If you take a look at floor plans, they're two-dimensional representations of the actual floors that are in buildings. They show you where the rooms are, how the measurements compare to each other, where the exits are, that kind of idea. The scale map, the scale on a map, scale tells us how the actual measurements compared to the measurements in the drawing. So the scale on a map says that 3 centimeters represent 2 miles. One idea that you want to take away from scale drawings is you're going to have actual measurements, those measurements in real life, and you're going to have those measurements that exist on the drawing. So one thing to always think about is, what are the drawing measurements and what are the actual measurements? So I always make a ratio table. I write the drawing measurements and I abbreviate. I just write draw, and then I write actual, and I abbreviate that by writing act. Now, what are the units that are involved in my drawing? Centimeters. And what are the units that are involved in actual real life? Miles. Now, I want to state that it's not always true that you are going to get the drawing measurements first, but typically the drawing measurements are going to be smaller than the actual real life measurements. So centimeters are much smaller than miles, so this must be the drawing measurement. I'm going to put the numbers that are associated with these units in the correct column. So 3 centimeters represent 2 miles. And what I'm going to do now is put all of the measurements inside of the table. So it says, what is the actual distance? So I'm trying to figure out what this is right here, the actual distance represented by 7 centimeters on a map. 7 centimeters on a map. Okay? And let's go to this question right here as well. What is the distance on a map? So that would be the drawing itself. So I want to find out what that is. That represents an actual distance, so the real life distance of 7 miles. So 7 miles would go right here. Now what I'm going to do is I'm going to figure out my scale factor. That means the number that I am multiplying 3 by to get the number 2. So what am I multiplying 3 by to get 2? Well, if I divide 3 by 3, I get 1. And then 1 times what number will equal 2? 2. So therefore, my actual, my scale factor to get from centimeters to miles is 2/3. So I'm going to multiply 7 by 2/3. And when I do that, I get 14/3. Or if I wanted to write this as a mixed number, I could also say that I had, how many 3/3 are in 14/3? There are 4 3/3 and then 2 more thirds. So 7 centimeters correspond to or represent 4 2/3 of a mile or 14/3 of a mile in real life. So if I had to answer this question, I could put that answer right here. 14/3 of a mile. And then over here, if I wanted to figure out the actual, the drawing distance for an actual distance of 7 miles, I would figure out what I have to multiply 2 by to get to 3. Well, if I'm starting at 2, in order to get to 1, I would divide 2 by 2. So 2 divided by 2 is 1. And then 1 times what number would equal 3? 1 times 3 would equal 3. So what do I multiply 2 by to get to 3? I multiply 2 by 3/2 to equal 3. If I'm doing that, this is going to be consistent. Every time I want to find the measurements for drawing, the number of centimeters in the drawing that correspond to the number of miles in actual life, I will multiply it by 3/2. So 7 times 3/2 is going to be 21 halves. So 21 halves of a centimeter, or how many 2/2 are in are in 21 halves. I can get 10 whole 20 halves and one more half in there, or 10.5 centimeters. So that's what this would correspond to, and that's what measurements I would put in here. So if you notice something about these numbers, these scale factors that I've multiplied by, anytime you want to go from actual to drawing, and then from drawing to actual, the scale factors are going to be what we call reciprocals of each other. Reciprocals are numbers that multiply each other to equal a product of 1. So if you had to multiply 2/3 by 3/2, you'd get 6/6, which is equal to 1. So if ever you want to go from drawing to actual measurements, you're going to multiply by some scale factor. If you want to go in the opposite direction, not in the opposite direction, if you want to go from actual measurements to drawing measurements, you multiply by the reciprocal of whatever that scale factor is. And in this case, it happens to be 3/2. All right, we have one more key concept to go through, and I hope as you're going through this video, you're writing down the key concepts inside your notebook. And the last key concept we're going to talk about, and you can pause the video if you need to copy the key concepts down. If a scale is, so remember, scale represents how the drawing measurements, how actual measurements are represented on the drawing. So when you deal with scale in a scale drawing, typically the first number is always going to be your drawing measurement. And then the second number is going to be your actual measurement. So what this is saying right here is, if I have a scale of 1 to 24, that means that the one unit in the drawing that I draw, that unit might be this right here, that unit might be this unit right here, but whatever it is, this one unit right here represents 24 of the same units in actual measurements. So in real life, if I draw this on paper, in real life, this segment right here is representing 24 of these segments put together. If I draw this length on paper, this length is representing 24 of these lengths in real life. Now, as you can see, it doesn't matter what unit I use, I just have to understand that I'm using the same units in both of these. So let's see, for example, this says I have a scale of 1 to 24. Let's see something at play here. So this scale doesn't have any units, but I can actually represent this same scale with some units. Let's think of a common measurement conversion that we use. We know that 1 foot equals 12 inches. We know that 2 feet represent 24 inches. So if, for example, I were to write down a scale of 1 to 24, and I drew an inch, this is 1 inch right here, this length right here would represent 24 inches in real life. So even though I'm given a scale of 1 to 24, I could say on paper that 1 inch in my drawing corresponds to 2 feet in real life, which is the same as 24 inches. And that's how you can see that one of these units that I've drawn actually represents 24 of these same units in real life. So when you're looking at scale without units, you want to think about this idea. This unit was all about scale drawings. Scale drawings involve two things you have to be really aware of. Scale drawings involve scale, which tell us how actual measurements are represented in the drawings themselves. And we also have to think about drawing measurements and actual measurements. And scale copies are copies of original figures that have their side lengths multiplied by the exact same scale factor, and all angles are going to be the same measurement. This unit is the beginning of a unit it's the first unit, but it ends our focus on scale drawings and gets us ready in thinking about what is this big idea that we've been talking about all along. And that's going to bring us into Unit 2. But for now, use these notes to review so that you are well prepared to show how much you know on your unit test. Have a great day and continue learning math. Math is life.